Okay, so welcome back. Today lecture is from section 16.2. 16.2 it's introduction to function. So last time we talked about relations. Relations are the we express relations using graph, equations, coordinates, and we were just showing the relation between x and y values. Now we're going to talk about functions. Functions are a special type of the relation. So let me give you the definition of a function. So this is the formal definition of the function. Giving a relation in x and y's, we're saying y is a function of x. Y is a function of x if for each element x in the domain, there's exactly one value of y in a range. Okay, so y is a function of x. So the second component, which is y is a function of x, if and only if for each element x, there is exactly one value of y in the range. So each x has assigned exactly one y value. So what that means, and this note will help you a lot, especially at the beginning when you have to decide if given relation is a function. This means that there is no two order pairs which have the same first coordinate and different second coordinate. So there is no 2 points, okay, which have the same first coordinate, the same x, however different second coordinate. Okay, so this is the definition of the function. Also, I like to add it another definition, which is very easy to memorize. What is the function? So definition of the function. Function means each input, which is x, has assigned only one output, which is y value. Okay, and make sure that the relation, it's a function, so make sure that we cannot have two different points which have the same x value and different y value. So that knows what that means right here. In function, okay, let me put that in red because that's important. X value can't repeat. This is the meaning of that node, okay? So there's no two order pairs which have the same first coordinate and different second coordinate. That means x values can't repeat. And you're going to see that based on the examples, okay? So here we have three different problems, okay? Three different relations, A, B, and C. And the question here is, we have to decide which of the relation defines y as a function of x. So y is a function of x. Let's go back to the definition. It means each input has assigned only one output. Okay, so let's check the first one. Okay, let's decide if the first relation is a function. Okay, so definition of the function is that each input has assigned exactly one output. So look what happened. 1 has assigned output 3, and also 1 has assigned output 4. So this is not a function. This relation doesn't satisfy the definition of the function that each input should have assigned exactly one output because, again, input 1 has assigned output 3, but also input 1 has assigned output 4. So this is the meaning of what I mentioned, that x can't repeat. Like you see here, x repeat, x has assigned two different outputs. So again, not a function because of input 1. Not a function because input 1 has two different outputs. Has two different outputs. Okay, so now let's move on to relation B. We have to decide if relation B it's a function. So definition of the function, each input have assigned exactly one output. So let me check this. Input 1 has assigned one output, which is 4. Input 2 has assigned one output, which is -1. And input 3 has assigned one output, which is 2. So this relation represents function. So this is a function. Yes. This relation is a function. Because each input has assigned one output. Okay, and the third one, we have to decide if this relation represents the function. So definition of the function, let me just rewrite this relation using coordinates points. Each input has assigned one output. So input 1 has assigned output 4. Input 2 has assigned output 4. And input 3 has assigned output 4. Okay, so definition of the function, each input has assigned exactly one output. So that relation satisfies the definition of the function. Each x has assigned one y value. So 1 has assigned 4, 2 has assigned 4, 3 has assigned 4. It's okay that all inputs have been assigned to the same y value. It doesn't matter. So but we definitely have a function here. Each input has assigned one output. And again, how you quickly going to know that relation is a function, what has to be satisfied, what you always have to pay attention that x coordinates can't repeat. Y doesn't matter. X coordinate can repeat. So nothing repeats regarding x coordinates. Okay, so this is a function. So you guys may think about students and a teacher. Every single student in this class has assigned one output, which is me, your teacher. So we are function because each student has assigned one teacher for this class, which is me. So it doesn't matter that you all share the same output, but each of you has assigned only one teacher for this class. So this is definitely a function. So make sure that you guys understand that. What the shortcut which I gave you, I mentioned that the x coordinates can't repeat. Okay, so like here in example C, x coordinates don't repeat. Like going back to example A, which we didn't have a function. Why we didn't have a function? Because input 1 had two different outputs, 3 and 4. So because of that, we didn't have a function. Okay. So here, just quick practice. This is number 1, number 2, number 3. We're not going to be very specific, but I quickly want you to decide if the given relation represents the function. So the answer for this one would be yes and no. Okay, so definition of the function, each input has assigned exactly one output. So first one, definitely yes. it is a function. Each x has assigned one output, one y. Now here, example 2, each input has assigned one output. So 4, it's been assigned to 2, -5, it's been assigned to 4, 0, it's been assigned to 0, 8, it's been assigned to 4. So definitely it's a function. Also, I quickly check, x don't repeat, so it's a function. Yes. Now, example 3, this is our relation, and we have to check if this relation represents the function. Each input has assigned one output. So look what happened. Here, input -1. Here, input -1 has output 6, and also input -1 has different output, which is 4. So this is not a function because the same input has two different outputs. Not a function. Because x equal -1 has two different outputs. So that's definitely not a function. Okay. So we're moving on. The next one, the next slide is about vertical line test. Vertical line test, it's the test which will help you quickly decide if the given graph, the given relation expressed using graph, if that relation is a function, yes or no. So how are we using the vertical line test? So when you have a graph, you just create vertical line, and if vertical line touch the graph once only, we have a function. If vertical line intersect or touch graph more than once, it's not a function. Okay, so vertical line test. Again, vertical line test. We have a function only if vertical line touch or intersect the graph once only. If vertical line intersect graph more than once, we don't have function. Okay, so here on this slide, you have a definition of vertical line test. If vertical line drawn through a graph of relation intersect the graph in more than one point, this relation cannot be a function. Okay, so how vertical line test works. So here we have a problem which shows you explain how vertical line test works. So we have a relation with the given set of order pairs 1, 3. Okay, 1, 3, 1, 4, 2, -1, and 3, -2. So now the question is if this relation represents the function. So what you're doing, you build the vertical line. Okay, so this is vertical line. And look what happened. This vertical line intersect the graph at 2 points. So it's not a function. Here we are good because the vertical line intersect graph only at 1 point. Here the vertical line intersect the graph only at 1 point. So here we are good. That could be a function, but because the first 2 points, 1, 3 and 1, 4, when we build the vertical line intersects those 2 points, so that's not a function. But also, you guys can quickly see, I gave you the shortcut that if the x coordinates repeat, we know that we don't have a function because input 1 has two different outputs, 3 and 4, so that can happen. Here, part B, this is a function. We have the relation given by the set of order pairs 1, 4, 2, -1, 3, 2. So I graph them, and now I create a vertical line. And at each situation, at each point, my vertical line intersect this graph, this point, only once. So we pass the vertical line test, which means this is a function. What that means that each input, each x has assigned different, exactly one y value. Each x has assigned exactly one y value. So we definitely have a function. Okay. So again, now since we know what is the vertical line test, so in next example on slide 6, we have to use the vertical line test to decide if the relation defines y as a function of x. Okay, so what I'm going to do, I'm going to draw vertical lines. Okay, here. So this is A, this is B. And look what happened. I don't need to do more. This vertical line intersect graph twice. So this is not a function. Not a function because vertical line intersects in the graph in more than one point. So we didn't pass. So we didn't pass vertical line test. Here in example B, I draw the vertical line. Okay, so here we good. My vertical line intersect graph once. Okay, you can draw more vertical lines. Here we also good. My vertical line intersect graph only once, so we good. And wherever I'm drawing the vertical line, each time my vertical line intersect graph only at one point. So we pass vertical line test. So yes, it is a function. Because vertical line intersect graph exactly only, let's put it that way, only at one point. Okay, so that's how the vertical line works, and it's very nice test because you quickly, when you see the graphs, you quickly can decide if the given graph represents the function. Next, what we're going to talk about function notation. We're talking about the function that y is a function of x if each input has assigned exactly one output. So we're saying that y is a function of x. Okay, just remember, y is a function of x. So function notation. First of all, when we talk about the function, you guys need to know that y is the same as f of x. Okay, so when we talk about functions, we're replacing that output with f of x. So we're reading that y is a function of x, and inside of the parenthesis, you have that input, which is x. So we just have to get used to of that, okay, of this notation. So here on this slide, I wrote it for you guys that when the function is defined by the equation, we often use function notation. For example, equation y is equal to x may be written as a function using function notation as, and like you see that y it's going to be replaced as f of x equal to x. So it's the same meaning. We know that f of x is technically y, but when we really want to use that function notation, we read that as y is a function of x. Okay, and that f just tells you that f is the name of the function. It can be g of x, it can be h of x. So we like to use the function notation. Don't forget that f of x, g of x, or h of x, which you will be seeing in different problems, that just gives you represents the output, which is y. So what is the meaning of function notation? That means the x is the input value from the domain of the function, and f of x is the function value, which is y value. F of x, it's y value, which corresponds to the x. Okay, and here, very important, I'm showing you to avoid the mistakes. So avoiding mistakes, make sure to know that f of x, it's not the same as f times x. Okay, this is f of x, which technically means y. Okay, so just we have to get used to that new notation because we're talking about the function. Function is a very specific relation where each input, each x has assigned exactly one output. So next what we're going to do, we're going to talk about evaluating the functions, which technically evaluating functions means finding the y coordinate for each input. Means finding y value, which means output, for a specific x value, which is input. So evaluating the function means finding y value for a specific x value. Okay? And don't forget, like we have when we graph the functions, you can graph x comma y. And don't forget that this is the same as x and y is just f of x. Okay, so this is that output. Y means output. Okay, so how are we going to evaluate the function? So first I'm going to go over the information which I wrote down for you guys in this PowerPoint. A function may be evaluated a different value of x. By replacing x, substitute x value from the domain into the function. And here, this is a nice example. For example, we have a function f of x is equal to x. And we need to evaluate this function for the input, which is x equal 5. So what we're going to do, we're going to substitute x with 5, evaluate, and we'll end up with 10. So f of 5 equal 10, that means that this function has a point, again, don't forget x, y. So when x is equal 5, we find the y value, we find the output, which is equal 10. So this is your f of 5. Okay, this is our f of 5. Okay, so we're going to do a couple examples, A, B, C, D. We're going to practice how to evaluate the function. Don't forget that the meaning of evaluating the function means finding the y value for the specific input. Okay, so let's do this problem together. So we have function g of x equal 1/2 x minus y minus 1. So again, we know the meaning that g of x is the same as y equal 1/2 x minus 1. Okay, so we need to do part A. We need to evaluate the function g of 0. G of 0 means find the y coordinate when x is equal 0. So remember that in the parenthesis, it's always x. So how we evaluate g of 0? We're going to replace x with 0. So we have equation 1/2 x minus 1, and we're replacing x always with the expression which you see. Okay, so we're going to have 1/2 times 0 minus 1, and I just follow the equation. So x from the equation was replaced with the number which you see inside of the parenthesis. So simplify, so we end up with 0 minus 1, which is -1. So we evaluate the function. So you can put it that way. So g of 0, it's equal -1, means that we have a point, again, x comma y, so this is 0, and this is y. We have a point 0 comma -1. Okay, so let's do b. We need to evaluate g of 2. So we're going to replace x with 2, and we have 1/2 times 2 minus 1. That will give us 1 minus 1, which is 0. So g of 2, it's equal 0. So the output is 0. That means that we have a point 2 comma 0. X is 0, the output is 0. And C and D, you guys will do the same way, so I'm just going to skip that. Okay, example 4, it's a little more advanced. Example 4, it's a little more advanced because, again, algebraically, it's the same type of problem. We still have to evaluate the function, and we have the function equation f of x is equal x squared minus 2x, which is the same thing as y is equal x squared minus 2x. And we have two different functions. We have function f with this equation and function g with different equation. So quadratic, this is linear, two different functions. And we need to find the function value. So what is different that in this case, your input, it's not a specific point, like 5, 7. Right now, like in part A, we have to evaluate the function when the input is t. In B, we have to evaluate the function when the input is expression w plus 4. And C, we need to evaluate the function when the input is -t. So, however, algebraically, we're doing exactly the same type of work. Okay, so let me talk about part A. So part A, the input, you need to evaluate the function when x is equal t. So like you see, the name of the function is f. So you're going to copy the equation of function f, which is x squared minus 2x. And you're going to replace x with t. Where you used to have x, you're going to plug in t. Okay, so we're replacing x with the expression which you always have inside of the parenthesis, which in this case it's t. So we will end up with t squared minus 2t, and that's it. That's going to be the answer. Okay, so it's not really a specific coordinates which we can plug in on the graph. It's just the expression, but we're doing the same type of work. In B, we have g of w plus 4. So again, expression inside of the parenthesis represents the input, so that's your x. Okay, so how are we going to do it? Okay, so we're going to copy, in this case, equation of function g, which is 3 times x plus 5 However, where we used to have x, we're going to plug in w plus 4. Okay, so we're replacing x from equation G with w plus 4. And just evaluate that. So we will end up with 3w plus 12 plus 5, and that will give us 3w plus 17. And part C of the problem, okay, in this case, we're going to replace x from function f with negative t. So don't forget that here we know that x is going to be replaced with negative t. So what I'm going to do, since you have f in front, that means we're going to work with function f. The equation of function f is x squared minus 2x. However, we need to replace x with negative t. So where we used to have an x, we plug in a negative t. And just simplify. So that will give us negative t to a second power, it's t squared. And negative will give you positive, plus 2t. So that's the answer. Okay. So the same type of work, I would say, we're still replacing x with the expression which you have inside of the parenthesis to evaluate the function, but in this case we have expressions, so we can't really graph, okay, like coordinate. Okay, so we'll move on. Here, the same type of problems. I'm going to skip the skill practice because it's the same type of problem. You guys can practice that at home. I can quickly just write down the final solution so you can just check if you solve it correctly. So g of a, the answer will be 4a minus 3. Here, g of x plus h, the answer will be 4x plus 4h minus 3. And the solution of 12 will be negative 4x minus 3. So go ahead, try to solve it by yourself and verify the solutions. Use solving those problems exactly the same way like we solve example for A, B, and C. You evaluate the function the same way. Okay. Okay, I will just... Okay, so we're going to continue. This is example 5. So next what we're doing, we're going to find function values from the graph. So we're going to evaluate the function value from the graph. So again, don't forget that finding function values means finding y values. Okay, so finding y values. So how are we going to do it? Hope you guys can see this graph well. Now, so let's talk about the first part. You need to find h of negative 1. So we need to find y value when x is equal negative 1. So you have a graph. So how are we going to do it? I'm going to find x equal negative 1, which is right here, and that's the point. Okay, that's the point. So we have a graph. We have a point negative 1, comma 2. So h of negative 1 means the y coordinate for the point when x equal negative 1, it's 2. Okay, because we have a point negative 1, comma 2. And you continue that way. Now find h of 2, which means find y coordinate for x equal 2. So technically, we have to find the y coordinate when x is equal to. So try to locate that point on the graph. So x equal to right here. So the y coordinate of that point is 1. Here we have a point 2, 1. So the answer will be 1. Okay. And you will continue. Find h of 5. H of 5. So the same thing. Find the y coordinate when x is equal 5. So locate on the graph point 5, comma, something. So we have to figure out what is the y coordinate for x equal 5. So when x equal 5, that's the point which have open circle. So let's talk about it. Open circle, that means this point does not belongs to the graph. Okay, so we can't evaluate. It's undefined because technically, okay, if the circle will be closed, okay, if the circle will be closed, we'll have a 0.5 comma -1, and the solution will be -1. However, since the circle is open, this point it's not, so 0.5 comma -1 is not part of the graph. So find h of 5 is undefined. So in cases like that, you're saying undefined. Okay, we cannot find it because it's not part of the graph. Now, part D and E, okay, we're doing the opposite. For what values of x? So now we're looking for x. H of x, it's equal 3, which means don't forget that h of x, you read that y, it's equal 3. So for what value of x? So we're looking for the first coordinate, y value, it's equal 3. So now I'm going to the graph, just use green. And I'm trying to find the point on the graph which has y coordinate equal 3. So this is 3 on the y-axis. So we will have a point here which has y coordinate equal 3. And this point has coordinates -4, 3. So they asking in part D for what values of x, y it's equal 3. So the answer will be -4. Okay. And for part E, for what values of x, h of x, which is y, it's equal 0. So here we have to find the x coordinate for which y value it's equal 0. Okay. So y value equals 0. So go back to your graph. This is y-axis right here. H of x means y-axis. Okay. Y equals 0 right here. So locate the point which has y coordinate equals 0, which is here and here. So we have 2 points. So we'll have 2 solutions. We have 2 points on the graph which has y coordinate equals 0. So the answer will be x equal -3 and x equal 4. Okay. So we'll continue. I want to go over additional problem like this, just to make sure that we understand correctly what we need to do. So here, let's talk about similar graph. Again, don't forget that open circle means we don't have a graph. It's not part of the graph. Closed circle means we including this point on the graph. So we have this is the graph of function f, okay? And you have to evaluate f of 0, which means find the y coordinate when x is equal 0. So when x is equal 0, this is x equals 0. Here we're talking about this point. This is 0, 3. So f of 0, again, don't forget that in the parenthesis, you always have x coordinate. It's 3. So the answer will be 3. Now find f of -2. That means find the y coordinate when x is equal -2. So when x is equal -2, I have a point here, -2 comma 1, which means the answer will be 1. Okay, so don't forget that here we're looking for the y coordinates. And find f of 5. So find the y coordinate when x is equal 5. So when x is equal 5, again, we have that open circle, which means it's undefined because of the open circle. And the remaining two problems, it's the opposite for what values of x. So now we're looking for x. F of x is equal 0. So don't forget that f of x means y coordinate equals 0. So find the point or points on the graph with y coordinate equals 0. So y coordinate equals 0 right here. This is y equals 0. Let me check if we have points. Yes, we do. This point has a y coordinate equals 0, and this point has a y coordinate equals 0. So for what values of x, y coordinates equals 0, -4, and the second one will be 4. And the last one, for what values of x, f of x, which means y, it's equal -4. So I'm looking for x coordinate of the point which y value is equal -4. So on the y-axis, find -4 and look for the point which has y coordinate equal -4. So that's the point, which is -5 comma -4. Since we have a closed circle, that means this point is on the graph. So the solution will be x equal -5. Okay. The last one, and I would say the one which requires the most work in this section, is finding domain of the function from the equation. Okay, so here with the domain, I will be giving you some tips because each function, again, linear function, we find in domain different way. Square root function, we find the domain of different way. So I will try to give you the hints for that. But first, let's just read the information which I gave you. So domain of the function, so consider function which is defined by the equation y is equal f of x. So that means y it's a function of x. The domain of function is the set of all x values that when substituted into the function, into the equation, produce a real number. So the domain is we listing all the x values for which we can always evaluate the function, which means find the output. Now, the range of the function is the set of all y values corresponding to the values of x in the domain. So the range of the function we're listing all the y values, okay, all the outputs. Now, algebraically, we definitely can find the domain from the equation. When we talk about the range, which is outputs, it's very useful to graph the function and just read the range from the graph. But here, first, we're going to focus on the domain. So to find the domain of the function, keeps the hints in mind. Exclude values of x that make the denominator of fraction 0, and exclude values of x makes the expression with a square root negative. Okay. So we'll talk about this problem, finding domain of the function. And what I'm going to do, since here I'm going to want to give you some hints. So I will just copy and paste that. That's the last slide. Let's see if I can see if I can copy that and paste. I'm not sure. Not really. Okay. No. Not really. Okay. No. Okay. Maybe I will be able to squeeze it. Okay. Here. So find the domain of the function. So here, what I like about this example because it has different type of functions. So we have 1, 2, 3, 4. So let's talk about first one. So first one, we call those type of function when you have a fraction, we call rational functions. So all the time when you have fractions, okay, so note. Functions with fractions. Which means rational functions. This is how you find the domain. To find the domain, make denominator not equal to 0. Because what we know about fractions, that denominator cannot be equal to 0. So to find the domain of these functions, what we're going to do, we always check what is in a denominator, which is 2x minus 1. And we know that that expression 2x minus 1 can't be equal to 0 because you never ever divide by 0 and solve this equation for x. So we have how you solve that. You're solving like equation. We adding 1 to both sides and we end up with 2x can be equal 1, divide each by 2, and we end up with x cannot be equal 1/2. So what that means? That means that domain is all real numbers except when x is equal 1/2. Okay, so that means that you always can evaluate this function, which means find y values for any x you wanted except 1/2. So if I will graph that, if I will have to write the answer using interval notation, so all real numbers except 1/2, you can write this down as set from negative infinity to 1/2, union 1/2 to positive infinity. So you always do the same type of work. So we always doing the same type of work when you have a function which have fractions. You set up that denominator not equal to 0. So technically, domain is the set of all the inputs. So for x, we can plug in any x we wanted except 1/2. So number 2, it's a little different. Okay. So it's also function which have a fraction. So I'm going to use, so this is also fraction. So I'm going to use the same information. So to find the domain, I'm going to make denominator not equal to 0. So again, when we see the fractions, so to find the domain, set up that denominator, which is x squared plus 9, not equal 0, and try to solve for x. So I will subtract 9 from both sides, and we end up with x squared is not equal negative 9, which what that means, x squared it's never equal to negative 1. Since this is true, this is a little tricky, but this is always true. We cannot really solve it. This is always true. Any x, any number, bring it to a second power, will never be equal to negative 9 because Positive number, bring it to a second power, will be positive. Negative number, bring it to a second power, will be positive. So this is always true. So when you have an equation which is always true, and we deal with those type of equations, when you solve something and this is always true, so the domain, is the set of all real numbers. Because whatever you pick for x, right here, you will never end up with 0. Even when you plug in 3. 3 to a second power will be 9 plus 9. That will give you 18. If you select for x negative 3, negative 3 to a second power will give you 9 plus 9, 18. This denominator will never ever be equal to 0. And how I know that? Because when I was trying to set up this denominator, and give the condition that denominator can never be equal to 0. And when I was trying to solve for x, when I end up with something what is always true, x squared not equal to negative 9. This is always true for any real number. So that means the domain is the set of all real numbers. Okay, so the domain, the set of all real numbers, using the interval notation, you can write from negative infinity to infinity. So you will be able to always find the y coordinate for any input. So you can just pick any number you wanted for x, substitute, and you always will be able to evaluate that function. That's what means domain. That's the set of all inputs. In this case, it's all real numbers. The third one, you guys need to remember this, is the square root function. Square root. So square root functions. When you have functions like that, square root, which we know the index of the square root is 2, which we're skipping. Or again, any functions which have a root with even index. Square root. Or any root functions with even index. You're doing the same type of work. So for example, like functions like that. This is what we always do. Not at index, even index. So to find domain of those type of functions, solve the inequality. Always. Expression, so I will just put it that way. Expression under the root greater has to be greater or equal to 0. This is the inequality which you're always solving, because we know that to find the square root or any root of even index, the expression which is under square root, okay, it has to be 0 or greater than 0. You cannot evaluate the square root when you have negative number under square root. So to find the domain of those type of functions which have square root or roots with even index, we always going to solve the inequality. So in our case, the expression under square root is t plus 4 has to be greater equals 0. Solve this equation for t. So we will subtract 4 from both sides, and we're getting t, it's greater equal negative 4. So what will be the domain? So I'm going to grab that for you guys. So right now in this function, the inputs are not x, it's t, but it's the same meaning. So t is greater equal negative 4. So hopefully you guys remember how to graph it. So that means we're including -4 and we're shading everything to the right side. Okay, so the domain of this function is going to be the solution of this inequality. So domain is the interval, closed interval, from -4 to positive infinity. Okay, so this function works only for t values starting from -4 and greater than -4. If you will try to evaluate the function and let's say plugging in for t something smaller than -4, like let's say -10, you will end up with the square root of -10 plus 4, which is square root of -6, and you won't be able to evaluate. So we always solve inequality to find the domain for the functions which have a square root with even index. Now, the last case is the easiest one, okay? So functions, okay, without, so this is nice one. Functions without fractions, square roots, okay? So the domain is the set of all real numbers. We don't need to do anything, all real numbers. When you have a nice functions without any restrictions, you don't see the function, you don't see the fractions, you don't see the square roots. The domain means the domain is the set of all real numbers, which is from -infinity to infinity, which means for x, in this case for t, you can choose any number you wanted and you always will be evaluate that function. So domain is the set of all real numbers, and that works for all linear functions, example like y it's equal 3x plus 5. The domain is the set of all real numbers. Quadratic functions, like let's say y it's equal x squared plus 5. The domain is always the set of all real numbers. Or cube root functions. Cube root functions. Like y it's equal cube root of x. The domain is also the set of all real numbers, because when you have a root with odd index, you can have under that root positive and negative. So cube root functions and root functions with odd index. Like example, y is equal fifth root of x. So the function like that, domain is all real numbers. Okay, I was able to squeeze that because I'm trying to keep everything in ones. So make sure that when you're solving problems and when you have to find the domain, that you guys will go back to that slide and just see how you find the domain, because again, how you find the set of all inputs, especially when you don't have a graph and you only have an equation. So domain, it's I would say the most important topic in this section 16.2, to find the domain of the function. So I want to go over to those problems also. 1, 2, 3, 4. Now, since you guys have notes, it should be a little easier to find it. I'm going to start with number 4 because look what happened. Number 4, we have a nice function, no fractions, no radicals. So linear, this is linear function. And I gave you the information that when you have a linear function right here, the domain of functions like that is the set of all real numbers. So domain is from negative infinity to positive infinity. Again, domain represents, and use the interval notation, domain represents the x values. It's a set of x values. So here in this problem, we don't have any restrictions. You can pick any number for x, plug it in, and you always will be allowed to evaluate that function. That means that's why domain is the set of all real numbers. Okay, now number 3, we have a square root. So square root, I mentioned to you. So to find the domain of the function which have a square root, we take the expression under root and we need to solve the inequality. That expression under the square root has to be greater or equal to 0. So square root function. So to find that domain, we solve inequality. Whatever is under square root, which is x minus 2, has to be greater or equal to 0. Solve that inequality for x. We're adding 2 to both sides. So we're getting x greater or equal to. And we need to express the domain using interval notation. So x greater or equal to. So we're shading everything from 2 to the right side. So the domain will be the interval from 2 to positive infinity. Okay, so that means this function, we only will be evaluate this function for any x's from 2 greater or equal to 2. Okay, so let's say when x will be equal to 0, you will end up with the square root of negative 2, which we cannot evaluate. So this is the domain. Okay, now going back to number 2. Number 2, you have a fraction. However, it's very similar to number 2 from the previous problem because that denominator has a x to a second power. So here, to find the domain of these functions, you have to give the condition that denominator of this fraction is never equal to 0, which means can never be equal to 0. So if you will try to solve that for x, you will subtract 1 from both sides, and you're getting 4x squared is never equal negative 1, divide by 4, and you end up with x squared, it's never equal to negative 1 over 4. And this is always true. Any number, bring it to a second power, it's always positive, so will never be equal to negative 1 over 4. The same thing, since this is always true, the domain is the set of all real numbers, which means from negative infinity to infinity, because we need to express the answer using interval notation. And number 1, here we have fractions. So you have to give the condition, that expression, that the denominator can never be equal to 0. Solve for x. So that will give you that x can never be equal 9. So x can never be equal to 9. So what that means, that the domain of this function will be any real number except 9. except 9. Okay, so you always will be able to evaluate this function when you will substitute for x any real number except 9, because when you will plug in 9, so look what happened in your denominator. You will end up with 9 minus 9, which is 0, with something like that we cannot evaluate. So how are you going to write this down using interval notation? So if you would like to graph it, this is all our inputs, our x values, okay? So that's graph. And we're saying that the domain, it's any real number except 9. So we cannot have that 9. So that's when we're using that open circle. So to graph something like that, so we can pick for x any real number except 9. So when you have to leave the solution using interval notation, you will see that here we have negative infinity. So we have interval from negative infinity to 9, union, and the second interval from 9 to positive infinity. So I don't think that you will have different type of functions. Also, maybe let me go back here. So the domain, when the domain it's all real numbers, when you guys don't need to do any type of work. So linear function, quadratic function, also polynomial functions. So I want to just give a note here. One note, because I didn't have enough space to write. All polynomial functions have domain all real numbers. So polynomial functions, that's the function, let's say y it's equal, when you can have a x, bring it to the higher exponent than 2. Let's say x to the 4 power plus 3x squared plus 7. So functions like that, which again, we're going back here. Again, I'm trying to give you enough information so you guys have all possible example which can happen on homework or on a test. So functions like that, also domain will be all real numbers, because look what happened. We can plug in for x any value we wanted, and we always will be able to find the y coordinate. We don't have here any restrictions. We don't have a square roots. We don't have a fractions. So when you have a nice functions, easy one, without radicals, without fractions, most of them will be the domain all real numbers. Okay, so that's it from section 16.2. Okay, so thank you for watching the lecture. Have a wonderful day.